Welcome to our online chemistry class. Myself Mukesh Kharge from SSPMS and Junior College, Shivajinagar, Pune 5. Our today's unit is biomolecules. In today's lecture, we are to discuss the carbohydrates. In this lecture, we are to discuss introduction of carbohydrates, classification of carbohydrates based on hydrolysis behavior, then based on solubility in water, then classification is based on reduction as reducing and non-reducing sugar. Then we have to discuss cyclic structure of carbohydrates, then types of disaccharide, sucrose, maltose, cellobiose, lactose. Let us discuss the introduction part. So general formula of carbohydrates are CnH2nOn. That means CnH2O n times. So initially carbohydrates are considered as hydrates of carbon. Hydrates means they contain water molecule. But nowadays there is no free water molecules. That means they are not hydrates of carbon. There are some compounds, they fitted that formula but are not the carbohydrates. For example, HCHO, that is formaldehyde, it fits into this formula when C1H2O 1 time, means N is equal to 1, but it is a simple aldehyde, but it is not a carbohydrates. Then if we write N is equal to 2, then our compound is CH3COH, but it is a acetic acid and it is also not a carbohydrates. So all carbohydrates are not fitting in the general formula which is given above. For example, rhamnose, it contains 6 carbon, 12 hydrogen, but only 5 oxygen. So it does not follow this formula, but still it is a carbohydrate. And there are some compounds such as formaldehyde, acetic acid, they follow this formula but they are not carbohydrates. So nowadays carbohydrates are optically active, means those compounds which can rotate the plane of plane polarized light either clockwise or anti-clockwise. They are optically active compounds. So carbohydrates are also optically active in nature. Polyhydroxy, poly means many, hydroxy means OH group, and they are aldehydes means they contain CHO function group, or they are polyhydroxy ketones. Ketones means C double bond O, means carbonyl function group, or they are also the compounds that can be hydrolyzed to polyhydroxy aldehydes or polyhydroxy ketones. So they are not directly polyhydroxy aldehyde or polyhydroxy ketone type of compound, but there are some compounds which can be hydrolyzed into that. Such compounds are also called as carbohydrates. So this is about the introduction part. Then next is the classification of carbohydrates. So we have to discuss the classification based on 3 different types. Let us discuss first one, and it is based on hydrolysis behavior. So here carbohydrates can be classified into simple or monosaccharides, or they are also known as glycose. So these carbohydrates cannot be further hydrolyzed. Examples are glucose, fructose, ribose. Then on the basis of function group, these monosaccharides can be classified into aldose. They contain aldehydic CHO function group, or they can be classified into ketones, means the compounds which contain ketonic function group dash C double bond O dash as a function group, or depending on the number of carbon atom, they can be classified into triose, contain 3 carbon, Tetrose contain 4 carbon, pentose contain 5 carbon, and hexose contain 6 carbon. The second subtype is complex carbohydrates, and they can be further classified into oligosaccharides, the carbohydrates which can be hydrolyzed into 2 to 10 monosaccharides. They are oligosaccharide in nature. And the another subtype is polysaccharides. They can be hydrolyzed into large number of monosaccharides. So example is starch, glycogen and cellulose. Oligosaccharides can be further classified into disaccharide. Di means 2. If complex carbohydrates which can be hydrolyzed into 2 monosaccharide, they are disaccharide. Example is sucrose, maltose, lactose. If oligosaccharide hydrolyzed into 3 monosaccharides, they are tri means 3 trisaccharides. Example is raffinose. Then if they can hydrolyze and they give 4 monosaccharide, they are tetrasaccharide. Tetra means 4. Example is starchose. So this is about the classification based on hydrolysis. The next classification is based on water solubility. So carbohydrates can be classified into two types. First one is sugar, another is non-sugar. If carbohydrates are soluble in water, they are called as sugar. Their another characteristics are they are crystalline in nature, they are sweet in taste, and they may be monosaccharide or oligosaccharide. If they are not soluble, means insoluble in water, they are called as non-sugars. Their nature is amorphous, they are tasteless, and they are polysaccharides. Example of sugar is familiar with the sucrose. It is soluble in water. Your common sugar, which is known as sucrose, it is soluble in water. It is crystalline, sweet in taste. It is a disaccharide. Then all are familiar with starch. It is an example of non-sugar which is insoluble in water. It is amorphous type. It is not crystalline and it does not have taste, and it is a polysaccharide. Then next classification is based on reduction. So whether your carbohydrates undergo reduction or not, they can be classified into reducing sugar and non-reducing sugar. So if your sugar reduces filling solution and tolerance region, they can known as reducing sugar, while if it does not reduce the filling solution or tolerance region, they are known as non-reducing sugar. So they act as a reducing agent or non-reducing agents. So if they reduces the sugar, they are monosaccharides and disaccharides with free aldehyde group or ketone group. Then and then they can act as a reducing agent, and they reduces the filling and tolerance region. Examples are fructose, maltose and lactose. But there are some disaccharides in which their bond structure does not give free aldehydic or ketonic group. So that aldehydic or ketonic carbon is bonded with another carbon. Example is sucrose, and it does not reduce the filling solution or tolerance region, and that's why they are called as non-reducing sugar. So sucrose does not act as a reducing agent. Okay, so detail about the reaction of aldehyde and ketone with filling solution and tolerance region that we will discuss in aldehyde, ketone and carboxylic acid. Okay, then next classification is Now I have to discuss the Fisher projection formula. So first, here we have to consider the Fisher projection formula of this compound. Now consider the longest continuous carbon chain, and that chain should be placed vertical. Now most oxidized carbon should be present at the top, and the horizontal lines bonds which are placed horizontally in your structure, they are projecting towards the forward direction, so which is shown with these solid lines, and the vertical lines in which that indicate the bonds projecting in backward direction. Okay, so this is the compound known as D plus glyceraldehyde, and this one is glucose, D plus glucose. So this is the Fisher projection formula of D plus glyceraldehyde and D plus glucose molecules. So these are the sign convention to write the Fisher projection formula of the compounds. Then next one is the optical isomers of glucose and the optical isomerism present in glucose molecules. So first one, there are some points related to this. Here we have to discuss first optical isomers of glyceraldehyde. So DL configuration system of optical isomers of glyceraldehyde. So here D and L configuration of lowest chiral carbon, that is C2 carbon, is considered only. This is the first carbon, this is second, and this is third one of that glyceraldehyde. So this carbon is chiral carbon because it contains 4 different atoms or a group of atoms. So D sugar, the hydroxyl group at the lowest chiral carbon, that is C2 carbon, on right hand side. So here we can see the OH group, that is hydroxyl group, on right hand side. So this is the D sugar, and if the OH group or hydroxyl group is present at the lowest chiral carbon center, that is C2 carbon, denoted by star on left hand side, then it is L sugar. These D and L sugars are only the symbols, and there is no relation of this with optical rotation. So optical rotation is totally depends on the rotation of that plane polarized light, either clockwise or anti-clockwise, when we pass that PPL through these compounds. If that compound rotate the plane of PPL towards the right hand side or clockwise direction, then it is dextro and it is denoted by plus sign, while if it rotate the plane of PPL towards the left hand side, then it is denoted by minus sign, and there is no relation of this D and this L with that optical rotation. So these are two enantiomers of glyceraldehydes. Enantiomer means optical isomers, and this is a glucose molecule in which the fifth carbon is asymmetric or chiral carbon atom, and it also rotates the PPL plane of PPL towards the right hand side or clockwise. So it is a dextrorotatory denoted by plus sign, and this D symbol because this OH group is on right hand side. This is about the optical isomerism of glyceraldehyde. Then next one is ring or cyclic structure of glucose. So glucose fails to undergo some of typical reactions shown by aldehydes. For example, Skipp's test. So aldehyde group shows Skip test when it react with Skipp's base, then it shows pink or red or magenta color, and this indicates that compound contain aldehydic function group. When it react with sodium bisulfite, then it also shows the addition product. For example, acetaldehyde react with sodium bisulfite, it gives acetaldehyde sodium bisulfite adduct, or when acetone react with sodium bisulfite, it shows acetone sodium bisulfite adduct. But even though your glucose molecules contain aldehydic function group, it does not show reaction with this Skip base and bisulfite, sodium bisulfite reaction. It exists in two isomeric form, one with melting point 146 degrees centigrade or 419 Kelvin, and other with melting point 150 degrees centigrade or 423 Kelvin. It forms methyl D-glycoside with methanol HCl reagent, and it contains only one methyl group. Then pentose and hexose can cyclize as ketone or aldehyde that react with a hydroxyl, that is OH group, at C5 carbon of that glucose. We will discuss this in next slide. The representation of that cyclic sugar are called as Haworth projection. So how to draw the Haworth projection, that we will discuss in next slide. Next one is the anomers. Cyclization of glucose molecules produces a new asymmetric center, and that asymmetric center is known as anomeric center at first carbon or C1 carbon. The two stereoisomers are known as anomers, and they can be denoted by alpha if your group is on lower side, and if OH group is on upper side, then it is denoted by beta. So the Haworth projection represents the cyclic sugar as having essentially planar ring with OH group at anomeric, that is C1 carbon. So alpha means OH group at lower side or below the ring, and alpha means OH group above the ring or upper side. You see the example. First one is alpha D glucose. This anomeric center, that is carbon number 1, that is the asymmetric center, new asymmetric center. Your OH group at below the ring, that means lower side, and in this structure OH group at upper side means above the ring. That's why it is called as beta D glucose. I think all of you understood the difference between alpha and beta anomers, and all are familiar with this structure. This is a 6-membered heterocyclic compound containing 1 oxygen and 5 carbon ring, and it is known as pyron. Now when the 5th OH will attack on first carbon of aldehydic function group of glucose, then we get a cyclic compound of that glucose, and it is similar to this pyron ring. That's why this cyclic glucose molecule is also known as glucopyranose, and this is the Haworth projection formula of that glucose pyranose. Then next one is the hemiacetal formation. So an aldehyde can react with alcohol and it form a hemiacetal. If an aldehyde and the hydroxyl part of same molecule react, then a cyclic compound is obtained and that compound is called as hemiacetal. So the hemiacetal group of glucopyranols is a potential aldehyde group and it imparts the reducing property to glucose. Thus, glucose gives positive tolerance taste and positive filling taste. Let us discuss the hemiacetal formation of your alcohol molecule. So this alcohol OH group contain one lone pair of electron. It will attack on carbonyl carbon of your aldehyde. Then when it form a bond with this carbon, then this carbon becomes pentavalent. So to make it again tetravalent, the bond between carbon and oxygen, that is a double bond, one electron pair goes to oxygen and oxygen becomes negatively charged. It will accept the hydrogen from that OH group of alcohol. So we get a compound ROCHROH and this compound is known as hemiacetal. So here if you observe the cyclic open structure of your 5-membered compound, so this is the first, second, third, fourth, fifth and this one is 6. So sorry, 5 carbon contain OH group on 5th carbon, so 5 hydroxy and first carbon contain aldehyde, so it is pentanol. So this OH on 5th carbon will attack on first carbon of your aldehyde group and the bond between carbon and oxygen transport to oxygen and it will accept the hydrogen. So this type of structure is known as hemiacetal and there is a formation of cycle in presence of H plus. So it is called as cyclic hemiacetal. And due to the presence of H plus, the position of equilibrium is towards the product side. It favors the product. So similar type of cyclic hemiacetal structure can observe in case of glucose molecule when the 5th hydroxyl group will attack on first aldehyde group and it introduce the reducing property to glucose. Glucose acts as a reducing agent and it reduces the tolerance reagent and filling solution. That means when your glucose molecule is boiled with tolerance reagent, that is ammonical silver nitrate, it shows silver mirror and you observe the silver appearance in your test tube, while when it react with filling solution and if we boil in hot water to that mixture, a red precipitate of cuprous oxide is formed and in this way it shows positive taste to tolerance reagent and filling solution. You can observe this taste in aldehyde, ketones and carboxylic acid topic. So glucose form an intramolecular hemiacetal as the anomeric carbon, that is C1 carbon, the aldehydic function group is present and the C5OH, that is hydroxyl group, react and they form a 6-member glucopyranose ring. And this glucopyranose ring, why the word is pyranose? Because that structure is similar to your pyran and there are two anomers alpha D plus glucose, that is alpha anomer. Why alpha anomer? Because the OH group at C1 carbon on the upper side of the ring, and beta D plus glucose, that is known as beta anomer, and it has an anomeric OH group that is on first carbon on upper side of that ring. Sorry, alpha means lower and beta means upper. So the right hand side group in Fischer projection formula are appears on alpha, that is lower side of the Haworth projection, and vice versa. So see the formation of glucopyranose ring. This fifth OH group will attack on first carbon of that glucose molecule, and the double bond between carbon and oxygen on this first carbon goes to oxygen and to take that hydrogen, and here there is a formation of hemiacetal ring which is similar to your pyran, and that's why it is called as glucopyranose. And that glucopyranose can be written in two different forms if this OH group towards the lower side, then it is known as alpha D glucopyranose. If that OH group on first carbon, that is anomeric carbon, is on upper side, then it is known as beta D glucopyranose. So remember the structure. Main question is asked, write the alpha D glucopyranose, then write down the OH group at lower side, and if you have to write the beta glucopyranose, then write down the OH group on first carbon to upper side. Remaining position of the groups in both these structures are identical. Don't change the position because it will change the molecule. So write down the compound as it is, which is given in these structures, and it is asked in your exam. So this is your Fischer projection formula, and this is the Haworth projection formula. So I will show you how to write this compound. We'll start from first. So here we'll change the position of OH, and on that basis we can write alpha or beta D glucose. Then you can easily mention the position. This OH, hydrogen, OH and OH, these three here, these groups on right hand side in Fischer projection formula, and see their position is OH, H and OH, they are on lower side. Okay, and the H, OH and H, which is placed on the second, third and fourth carbon respectively on left hand side, they are on upper side in our projection H, OH and H. Okay, only the change in the position of newly created OH group on anomeric carbon, that is first carbon. Okay, so in this way you can easily remember the Fischer projection formula is converted into Haworth projection. Then ring cyclic structure of fructose. It is similar to your furan ring. It is also heterocyclic 5-member aromatic ring, contain one oxygen and 4 carbon. It is aromatic in nature. So the fructose structure in Fischer projection formula is like this. Here ketonic group is present on second carbon, so your fifth hydroxyl group will attack on this ketonic carbon, that is second carbon, and there is a ring between the second carbon and fifth oxygen. So it is a 5-member ring and it is similar to your furan, that's why it is fructofuranose, and it is also a hemiacetal ring, so you can write that Haworth projection formula. So this is your linear D fructose structure, and the compound in house projection is the D alpha D fructofuranose. So here OH to lower side, and the first carbon is CH2H as it is. So fructose forms 5-membered fructofuranose ring by reaction of C2 ketone group with hydroxyl group on C5 carbon. The next one is the disaccharide. So disaccharide gives two molecules of same or different monosaccharide on hydrolysis with dilute acid or specific enzyme. Examples are sucrose, maltose, lactose, and silly oil. So the two monosaccharides are linked together by an ether oxide linkage dash O dash. That linkage is called as glycosidic linkage. So in the classification we already discussed the reducing sugar, the sugar that is alpha hydroxy keto compound, which reduces the filling solution and tolerance region. That sugar is called as reducing sugars. That is a reducing agent. Example is fructose. And those compounds which does not reduces the filling solution and tolerance region, they are called as non-reducing sugar. So here we have to discuss the sucrose in detail. It is also a cane sugar or table sugar. You can observe the glycoside linkage here. The formula is C12H22O11. There is a glycoside linkage between C1 of alpha D glucopyranose and C2 of beta D fructofuranose ring, and it is a non-reducing sugar. The aldehyde and ketone groups of both monosaccharides are involved in the formation of glycosidic linkage. So there is no free aldehyde and ketonic group in your compound. So it is a non-reducing sugar. And if it undergo hydrolysis, the D plus sucrose, the optical rotation is plus 66.5 degree. If we hydrolyze this with enzyme invertase, it gives two molecules. One is D plus glucose and another is D minus fructose. The Leo rotation of fructose, which is minus 92.4 degree, is larger than dextro rotation of glucose, which is equal to plus 52.7, and that's why the overall molecule, that is product rotation, is towards the left hand side anti-clockwise, so it is negative, and your original compound, that is D plus sucrose, it shows plus rotation. So after the hydrolysis, the product is overall rotation is reverse, so it is called as invert sugar, and the process is the inversion of sugar. Then maltose formula is C12H22O11. It is obtained by partial hydrolysis of starch. Okay, and if you observe the glycoside linkage between glucopyranose ring, that is C1 of first alpha D glucopyranose and C4 of second alpha D glucopyranose ring. Then if you observe the on hydrolysis with dilute acid or enzyme, the enzyme is maltase, it gives two molecules of glucose. And here if you observe the structure Howth projection of this maltose, the second ring contains the OH group. So the hemiacetal group at C1 of second ring is not involved in the formation of glycoside linkage, and it is free in nature. So a free aldehyde group can be produced at C1 carbon in this second glucose molecule. So it produces a aldehyde group, so it can reduce the filling solution and tolerance reagent. So that's why maltose is a reducing sugar. Such a type of free aldehyde group cannot be produced in sucrose. So it is a sucrose is a non-reducing sugar. And next one is the cellobiose. Formula is C12H22O11, and it is obtained by partial hydrolysis of cellulose. Now if you observe the structure of this cellulobiose, the first carbon of first glucopyranose ring of beta D glucopyranose and C4 carbon of beta D glucopyranose ring of second molecule, it form a linkage and it is upper side, so it is known as 1,4 beta glycoside linkage. Again if you observe the structure carefully, the second molecule in which the first carbon contains free OH group. So hemiacetal group at C1 of second ring is not involved in the formation of glycoside linkage. It is free in nature. So a free aldehyde group can produce at that C1 carbon in the second glucose molecule. So it is also a reducing sugar because it reduces the filling solution and tolerance reagent. So cellulobiose is also a reducing sugar. Then lactose. Formula is C12H22O11, and it is also known as milk sugar. If you observe the structure, so the C1 carbon of first beta D glucopyranose, galactopyranose, and C4 of beta D glucopyranose ring of the molecule form a glycosidic linkage, and it is beta 1,4 linkage because first carbon of first ring and the fourth carbon of second ring, they form a linkage. That's why it is 1,4 linkage. And if you observe the structure, the second molecule in which C1 carbon, the OH group is free. So hemiacetal group of at C1 of second ring is not involved in the formation of glycoside linkage, but it is free. So a free aldehyde group can produce at that C1 carbon in second glucose molecule. So it is a reducing sugar and it reduces filling solution and tolerance reagent. So this is about the carbohydrate. Thank you for watching my YouTube channel Mukesh Kharge. If you like this video, you can subscribe and share. Thank you very much.